Here we have 2 moles of SO2 and 3 moles of NO2 reacting to produce SO3 and NO in a 2-liter flask. The question asks us to find the equilibrium constant, or Kc. The first step here would be to rewrite the equation and check if it's balanced. Since our equation given here is already balanced, we don't have to worry about that part, but we can rewrite our equation. So we have SO2 reacting with NO2 to give SO3 and NO, or nitrogen monoxide. Our next step would be to set up our ice table. So since we're dealing with concentration, we're going to have concentration of I, or initial conditions, change, and equilibrium. Now, according to our question, initially we have 2 moles of SO2 in 2 liters. So we can use the formula concentration equals moles over volume and say that our concentration initially for SO2 is going to be 2 divided by 2, which is 1 molar. Next, for NO2, initially we had 3 moles of NO2 in 2 liters container. So similarly, we're going to have our initial concentration as 3 divided by 2, or 1.5 molar. Now, initially, we do not have any other information, so we can say that there was no SO3 or NO present in the flask initially. Next step would be to set variables. Remember that we have to add x, or if we consider our variable to be x, which is what we're going to do, let it be x, we can add x to the product side for change, and for reactants we subtract x. So for our change for SO2, we're going to have negative x because it's on the reactant side and there is no coefficient with SO2 other than 1. So for NO2, we'll have the same thing. We're going to have negative x. For SO3, we're going to have positive x. And for NO, we're again going to have positive x because they are our products. Next, we move on to the equilibrium concentration. So we know that equilibrium concentration is equal to the initial condition or concentration plus the changed concentration or the conditions. So we're going to have 1 minus x for SO2. For NO2, we're going to have 1.5 minus x. For SO3, we're going to have x. And for NO, or nitrogen monoxide, we're going to have x again. Now that we're done with the first part, setting up the ice tables, we can move on to the next part. So based on the question, we see that at equilibrium, 1.5 mole of nitrogen monoxide is present in the same container. So we clearly know that the equilibrium concentration of nitrogen monoxide then will be 1.5 divided by 2, which is the volume of the container, which will give us a concentration, or equilibrium concentration, of nitrogen monoxide as 1.5 over 2, or 0.75 molar. So let's write it down here, different color. So at equilibrium, we're given that the equilibrium concentration of nitrogen monoxide is actually equal to 1.5 divided by 2, which is equal to 0.75. Now, based on the question, according to question, they already gave us that x equal to 0.75. So that is exactly our final concentration for nitrogen monoxide. So we plug the value of x into all of our equilibrium variables, and we get the remaining concentrations at equilibrium. So for SO2, we are going to have equilibrium concentration of 1 minus x, which is equal to 1 minus 0.75, which is 0.25 molar. Next, for NO2, we're going to have 1.5 minus x, which is 1.5 minus 0.75, which will again give us 0.75 molar. And then once again, SO3 also has the variable x and nothing else. So when we say, like, well, what is the concentration at equilibrium for SO3? We can easily find, or say that it's equal to x, which is the same as nitrogen monoxide's concentration, which is 0.75 molar. Now that we have our equilibrium concentrations for every single reactant or product, we can plug them into our equation for the equilibrium constant Kc. So Kc is going to be equal to our products raised to their coefficients divided by their reactants and their coefficients. So we will have, as our products, we have SO3, and then we have nitrogen monoxide, and then we have SO2, and we have NO2. For the units, so we are going to have n times m over m times m. They all cancel out, so we will have a unitless equilibrium constant this time. So we're going to have, for SO3, we know it's 0.75. Multiply that with the value of NO, which is, again, 0.75. Divided by, for SO2, we have 0.25. And for NO2, once again, we have 0.75. Before we plug everything into our calculator, we can cancel two of them out. And we end up with our Kc value of just 3, which is the answer that we're looking for. Let us now move on to another example, which is very similar to the one that we have just done now. And the only exception to that example is going to be that instead of dealing with concentrations, we're going to be dealing with partial pressures and the equilibrium constant for partial pressures, or Kp.